everyone. Don't let this stuff overwhelm you. We'll be covering sections 11.3, 11.4 today. We got the integral test, we got the comparison test. Also in 11.4 is something called the limit comparison test. So we'll start out with this integral test, which is just awesome. Because with the integral test, all we have to do is look at this series that they have for us. If we know how to find the integral, we turn it into an f of x. We know everything's in terms of that. And if we know back from improper integrals whether that integral diverges or converges, then we can talk about the series as well. So that's what you see here. We're saying, well, the first thing we got to make sure, though, we got to make sure f is continuous, it's positive, and it's decreasing for n greater than or equal to 1. So we do have to ensure that. We'll make sure we'll check that. Then we'll just check if the integral converges, then the series will converge. If the integral diverges, the series will diverge. And so far, how many tests have we had? Well, we've covered the geometric series test, right? I know this stuff starts building, but we just stay organized. And we covered tests for divergence, right? Geometric series is something like, 5 times what? 0.3 raised to the nth power, n equals 0 to infinity. I mean, this is an example of geometric series. That's an example of a geometric series. Everyone see the exponential expression? Cool. Keep in mind, if I just add like an n here, or an n factorial, it's not geometric. Cool. But that's an example of geometric series. Test for divergence. Great test where we just look at the sequence, and if the sequence, the limit of the sequence is not equal to 0, then we know that the series got to diverge. So these can even come into play. We might look at something like that even today. But we'll start with this integral test. We'll look at a problem that we're all very familiar with. How about that series? Now, it was the last thing I covered in the last lesson. The last thing. There's a name for this series. It starts with an H. You know what they call it? It's a harmonic series. But you'll notice that the harmonic series always diverges. And you can do it by the integral test. Because think of what's the integral? And we said, all right, I went from 1 to infinity of 1 over x dx. And we explore that integral. It's an improper integral. But we know whether or not that converges, diverges, it tells us about this. Because everyone, these checks hold true. That's a continuous function. It's always decreasing for n greater than or equal to 1, right? It keeps getting smaller in terms of the values. And all the terms are positive. You recall what happens with this? What's the integral then? Natural log of x. Let's see. No, wait. And I'll replace that just with t towards infinity. We came out when we did this. We got something like that, right? And then you plug in a 1, you get the natural log of what? 1, what's the natural log of an infinitely large number? This diverges. Cool. But, what about this one? And I say, again, we know how to do that integral, true? Terms are positive. If terms are decreasing, and the function is continuous, check that out. I'm not writing all the notation here, but let's explore that integral. And if it converges or diverges, it'll tell us about this series, whether or not that converges. Cool. Is this right? It's my worst fear. Good. Everyone's telling me no, 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 no. How do you do that integral? Not a use sum. Well, we think of this as x to the -2. The integral of x to the -2 is x to the -1 over negative. And we get a -1 over x. So I'll go back and put a little t here and go from 1. We'll do the limit as t approaches infinity. And what happens to this dude? Yeah, you put in a t, you get the limit as 1 over t. You need that limit. Katie says that's going to 0. Subtract the limit as t approaches infinity of -1 over 1. Well, what's that just going to be? Subtract, we don't have to put all that in writing. Subtract the -1. That limit's 0, right? So what's 0 minus -1 equal? one. So this series converges. Now, does it converge to 1? No, it just converges. That's what we know. What's the only test we know so far that gives us, we know a value that it converges to in terms of these series? The geometric series test, right? That's the only one that has a formula. And you can look at that summary sheet. It's the only one where you have some actual formula that we can say, oh, it converges to this value. With these, we don't know what the value is. So today, you'll notice we'll estimate. We can estimate what the series is going to converge to. That's the best we can do. Even to this day, it's not like, someone proved this, we figured this out, and we'll talk about that. But that's what's so neat about series, is how we just know it converges. What it converges to, we can estimate. We can estimate, especially with technology. Is everyone okay with this? Hey, these seem to come up a lot, so we can just call them a p-series, right? So I'm going to walk over here, and let's call these p-series. And we'll talk about that power of p. What if the p is greater than 1? What will always happen? It's going to converge. I mean, there's two examples to look at. What if the p is a 1 or lower than a 1? What's going to happen with these? It's always going to diverge. And you can actually call it a p-series. So when it comes to a justification, I remember we were talking about that yesterday, kind of with the what to write down or justify. You could say, hey, I already know that this is going to diverge. You can say this is the harmonic series. But you also might say, well, it's a p-series, p equal to 1. And you know that that's going to diverge. Make sense? You could say, hey, this converges, and your justification, Juliet, all you have to say is, this is a p-series. And the p equals 2, which is greater than a 1, so you know it converges. And then you've used this actual, p-series test. But what's so great about the integral test, this works for all integrals as long as the function is continuous, positive, decreasing. So let's look at some other crazy series. All right? Awesome. By the way, could you also just recognize that's a harmonic series? Nice. Hey, on that note, do you remember? I did this in a class, but I want to do it again. I think there was one in the homework like this. How about 50 over 8? What's going to happen with that? That will also diverge. Isaac, excellent. This is just a constant multiple of a harmonic series. Or you can use a p-series test. So this also diverges. All right. Okay, let's check out some more. Great job with that. Okay, here's my first example. Summation n equals. They either start these things at 1s or 0s, and when I'm in 11.3. Okay. I'll start with that. Is that a p-series?
Yes. C.
So I can take the 10 out and think of this as 10 times 1 over n to the 1/5, right? Someone agree? What do you know? I mean, I don't even have to do the integral test. This is a p-series. What do you know about that p-value?
Diverges.
It's a p-series. The p-value equals 1/5, which is lower than 1, and I heard it, this series diverges. Well, it's 10 times this. Yeah, well, it's a constant multiple of a p-series, if you want to write it. This is a constant multiple of a p-series right there. And we know that that's going to diverge. We also could have done the integral, right? The integral test. And I'm going to wait till you're done, and I'm going to write something down that's going to look familiar. Okay? I see some people are copying. Okay, I'll just put a wall here. How about this problem? Well, I got a 5 up there in the right. I want you to think about it. And then someone's going to tell me, hey, professor, they're going to recognize something. So when I got This is the last problem. We said it diverged. Now I wrote up this problem. Do you see something going on? You see it, Dave. What's going on? It's the same thing. I love it. I want to recognize it because these are the same. It's just written in different notation. It's in that radical notation. So if you're like, oh, can you give me a quick review on this? Think of that as the R value and think of this as the E value. And we're saying that N in the denominator is to the E over R. The exponent is a 1, but what's the radical? A 5. So 1 over a 5. Because there's an invisible 1 over it. But that's one thing. That's what can throw off the student. That's exactly what can make a student go, oh, I don't like these series. It's like a prerequisite skill that they're not recognizing that these are the same. So you can look at the P series.
So, by definition, that anything that has a radical in the denominator automatically
Yeah, but what if they do a radical and then they what? They stick it and you see that this ratio, they do something with a power there, and now it's to the, right, I'll do, how about a 7? So now you're like, uh-oh.
You got 7/5.
Now you got 7/5. What's going on?
Then it's,
So great point, Dave. I just want to be careful they did something like that. I don't know if I saw anything like that in the book. But it's a good eye thinking about the radicals down there. Aaron, that was great. I was trying to. Everyone, this is like number 7 from 11.3. And I want you to treat this problem as if they start at 1. They did. I'll start at 1 too. N over n squared plus 2. They had n over n squared plus 1. Section 11.1 to 11.6. Don't let it intimidate you. We would just always stay organized. What tests have we had so far? I'm looking at this problem. I'm like, let's pretend we didn't know it was in section 11.3. I'm like, what series test am I going to use? You can really just go to a checklist. Is that thing a geometric series? No way. That is not geometric. Can I use the test for divergence? So let's explore that. Test for divergence is an awesome test where you hide the series, you think of the sequence, and if the limit of the sequence isn't 0, you're going to know that the thing diverges. Well, unfortunately, when look at that carefully, what's the limit of that sequence? The limit of that sequence is 0. Do you follow me? So I can't use test for divergence. Let me say it again. I want to make sure people's clear with that. I can't use test for divergence because the limit of that sequence is 0. You're going to find a lot of these sequences they have here. Remember, a series is a summation of the terms of a sequence. A lot of the sequences they have there, the limit's already 0. So you won't be able to use that test for divergence. Okay? So, these are out. Well, what did we learn today? Oh, the integral test. So, hey, let's give this a shot. Do you not integrate something like that if we put x's on it and stuff? Let's check it out. X over x squared plus 2 dx. Hey, I will make sure of a few things. That's a continuous function, check. It's decreasing for n values greater than or equal to 1. And the terms are positive. I think we can work this out. How do you do that integral though?
You said.
You sub. Maybe that's the biggest challenge to 11.3. When it comes to how do I do the integral? Do I do the u sub? Don't need a u sub, or do I need, integration by parts? Okay.
You can also separate them, I guess.
You can't split that one up. You were thinking of something like this. So you can't split that up. So we're going to let u equal x squared plus 2. And du equals 2x.
There you go, Katie.
And we rock out that u sub. Hey, eventually I'll write down the limit as t goes to infinity. Just trying to save some writing, true? I go in there, what does this knock out? Let's go on. You get a half, right? You get an integral. 1 over what letter? Well, what's the antiderivative of 1 over u?
Natural U.
Very good. All right, I'm going to put my u back. Okay, what was u? Hey, do I have to put the bars? Well, how do you know that that's already positive, right? So I will, just to be curious, if those bars bug you sometimes, I can soften these because x squared plus 2 is always going to be positive, right? When I plug in any value. And we're going to go from 1 to, all right, now I'll put the t and write the limit as t approaches infinity. It's an improper interval. And some of you already can tell. You already know the answer to this thing. Look what's coming up, another natural log. What happens when you get a natural log? 1/2. You're going to think of this as what? Some infinitely large number, right? And then what happens? You plug that in there. So you get an infinite, I'll just put it, you get an infinitely large number when you plug it in here. Subtraction, then you get the limit as t approaches infinity. You plug in a 1, you get 1/2 of what? And the log of 3. Yeah, but this is approaching what? Infinity. It's the natural log expression. So this series right here, unfortunately, it does not converge to a value. It diverges by which test?
Integral test.
And I'll just put IT. If you like to abbreviate, do the same thing on anything. Integral test, IT. Geometric series test, GST. Test for divergence, TFT. You don't want to write on it. Here's my justification. If you want to go in and show that that limit does approach infinity, that's fine. Cool. Hey, have you noticed this wasn't a P series? So I had to go through the integral. Well, it wasn't too bad, was it? Nice. Nice job. Hey, any other weird integrals in here? How about 1 over 2n plus 3 cubed. How about that? This is the integral test. It's a rock and roll test because we already know about improper integrals. And we're thinking, well, to approach this problem, is that geometric series? Heck no, right? The key about geometric series, it's exponential. It has to be everything to an nth power. Or it can have a constant multiple with it, right? When I'm writing, I'm talking about geometric series, look stuff like this. 20 times 2/3 raised to the n plus 1. It can even have a -1 to the n. This is what I'm talking about when it's geometric. Exponent. This is not geometric series. Well then let me try test for divergence. Can I use that? So let me hide this. Does anybody know the limit of that sequence as n approaches infinity?
0.
It's 0. I can't use that. See, you're going to notice that a lot of the sequences, the limit's 0, so you can't use test for divergence. But boy, if you notice that sequence right here, the limit isn't 0, you're going to be done with the problem. You're going to be like, this series diverges by test for divergence. So we're left with which one that we've learned today, the what? Integral test. So that's what I mean. You kind of go through a checklist. Well, who knows? You might want to try integral test first. All right, let's try it. Okay, all the terms of this series are positive. Oops, I'm going to make that an X. They're decreasing. We can use the integral test. How do you do that integral? Any idea? Nah, because of 2x plus 3. To be a P series, you'd have to just have like an X.
So it just has to be one variable and it can't have constants?
That's right. I know. But hey, we'll just do a what? But it is to the third power, which if it was a P series, it would converge. Maybe that gives us a heads up on what's going on. Because we're really just doing a use up to it. Isn't that good? So very good. I love it. So we have a hunch. We think this is going to converge. We think this series converges, but we're going to show all this.
So like after we do the use of when it's u to the third, can we say it's a P series then?
Not then right there because we'll put this back. But you get it. You're like, we know what's going on by the integral test.
Right.
Just like this baby, it's going to converge.
Okay.
But I love that you recognize it. Just because we have to put that back in there. What's that now?
1/2 u equals yes.
Okay. Half over here. And how do you do that?
U to the negative 3.
Good, u to the negative 3. And then that becomes what?
U to the negative 2.
U to the negative 2 over negative 2. So u to the negative 2 over negative 2 becomes a...
Negative 2 over u squared.
Yeah, and I can move that now back to the bottom, right? Is that okay with that, right? U to the negative 2 over a negative 2. With that 2. Maybe I should just write that. I don't want anybody to get confused by that. Sometimes those antiderivatives, that's what bugs the student. Just doing some simple thing like that. That becomes u to the negative 2 over negative 4. Which can also be written as what? Negative 1/4. And I can put what in the denominator now? I gotta make sure it's squared. 2x squared. Now I'm now gonna write the 1 and the t. And I'll say, what's the limit? As t approaches infinity. But Connor, just like we thought, what's going on when you put an infinitely large number here squared in the denominator? It's gonna converge. So you're gonna get the limit as t approaches this. You're like, this will go to, what will this go towards? I'll write it out first. And as t approaches infinity, a negative 1/4 to t plus 3 squared minus a negative 1/4, plug in a 1. So what happens when you plug in a 1? 2 times 1 plus 3 is 5. What's 5 squared?
25.
Alright. And a minus minus is a what? Plus. Now when we know what's going on with that baby. That's going to 0. True? This series is converged, just like we expected. Now, do I have to write this number down that it converges to this? What is that, 1/100? Do I say this series converges? No, we don't know what's converging. The only way we could estimate what it converges to by the remainder theorem. We'll do the remainder theorem in a second, it's fun. But we just right now can say this converges by which test? By the integral test. Justification, right there. I've got it right there.
So if one of these series doesn't fit into the text, you just take the integral of it?
Yeah, from so far. But what
Yeah,
if,
so far.
but eventually you're gonna run in a jam where you go, all right, I checked geometric series, it wasn't geometric series. I can't do test for divergence because the limit of the sequence was 0. And then you're gonna look at it, Katie, and go, I don't know how to get that integral. So you're gonna go to another test, which would maybe be the comparison test, where we just compare it to something you gotta do an integral to. So it's kind of fun. Don't make it like, oh, it's fun doing this. And a great job with that. Before we do the remainder theorem, I have to give you one like this. I want to see what you all think. Does anybody know? Oops. I'm going to put the series first. So this is off your point there, Katie. Something like, oh, the book had a 4. I'm going to use a 9. I'll use a 9. How about that? I want to determine whether or not this series converges or diverges, and use one of the tests. Well, can I hide this again? What's the limit as n approaches infinity of that sequence? 0. I can't use test for divergence. Is that a geometric series? Heck no. So now we're left with integral test. But do you know how to do that integral? That's the question. I bet a lot of you do. It's not an integral we see often. Does anybody, so before I do this, can we talk about this guy? We all know this one. That's a special integral. It's one of the inverse trig functions. Which one is it? R2. That's arc tan of x, isn't it? That's what everyone had antiderivative is arc tan of x. Oh, it's not. Yeah, but isn't this like an arctan? So then how do you do the integral of like 1 over, I'll use a different example. How about 1 over x squared plus 4? has a little formula to it unless you want to do some, manipulating the math and doing a U sub, which would be fine. You know what this turns into?
1/2.
1/2 arctan of x over 2. I'm thinking of that as a squared. Because we say the integral of 1/x squared plus a squared will always turn into 1/a arctan of x over a. And you could actually justify that by doing a U sub. Some of you like to do that. But this, if you recall, do you remember when this emerged? This was in the partial fraction section. This right here emerged in section 7.4. So what we're saying is here, Katie, we're like, okay, I can do the integral test if I know how to do that integral. Something else. We gotta know about the behavior of this because we gotta look at a limit, don't we? Someone, can I draw the arctan graph for you? We haven't seen it too often. What's tangent of y equal to tangent of x do? Bunch of these, like whoop, 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 right? You know what the arctan graph does? It's got two horaxes. And it looks like this. This is y equal to arctan of x. Just something for you to note so we can answer this problem. This is y equal to arctan of x. And this is pi over 2. This is negative pi over 2. Anybody want to try it on your calculator just to look at it? Put it in your calculator, just check. Just in case you were curious. You hit y, hit the inverse, where you got to hit second tan. That's the arctan graph. Anyways, is this approaching some value in terms of the limit? Yeah, so that's going to help us out when we do this problem. Cool. Hey, good news. Good news. If you freak out doing a problem like this, and you're like, I don't know how to do the integral, don't worry, we got more tests coming up. Okay? But I would like to do it with you because it's not too bad of an integral. So let's try this one. What is the integral of 1/n squared, or x squared plus 9? What is that? 1/3 arctan of x over 3. Now I'm going to go back and put my 1 in my t, and we're going to take the limit as t approaches infinity, right? Now, and by the way, arctan of x over 3 would behave very similar to this. It would still approach a pi over 2. I can leave this up. I'll put a plus constant. Okay, what do we get? The limit as t approaches infinity of 1/3 arctan, I'll put the t in there, minus, I probably got 1 in there, 1/3 arctan of what? 1/3. So and what is this limit? And you go, will it behave just like this? Just like it. Just like this. It will still approach pi over 2. And I did this because this is approaching an infinitely large number, right? So this right here is approaching 1/3 of what? 1/3 of, what is that? Pi over 2 minus 1/3 of arctan of 1 over 3. And Connor, I'll just write that out. This is actually the value of that limit. But it's convergent to a number. So what do I know about this? This converges, and what test did I use? By the integral test? But don't let this bug you, everyone. It's because the graph of arctan. You can look at it that way. Cool. Hey, can I erase? Awesome. So on that note, I'm looking at some eyes, people are going, ooh, that problem could get, because that integral's kind of weird, right? Well, no worries, we got a cool test called the comparison test. And what you do is, you know what made this problem challenging, Katie and everyone? That stupid plus 9. So what we'll do is, we'll compare it to something like 1/n squared. And isn't 1/n squared a p-series? So you may love this test. It can get you out of the jam when you're dealing with an integral that's either annoying to you or just bugging you. Cool. Hey, before we do that, before we do comparison tests, and I think we should do that problem. We should do that exact problem. I would like for us to use this remainder there. So what we're going to do is, you and I are going to estimate what this sum is, right here. N equals 1 to infinity, 1 over n squared. Can you help me at least estimate what that is? Oh, by the way, if you wonder what problem I'm using number 37 out of the textbook. They go, well, how many terms they want you to use? They say, can you use the first 10 terms of the series? And they want you to use 10 terms to estimate what the sum is. So what does that mean? I gotta do a what? I'll start writing it out. The first term would be plug in a what? 1 over 1, that's the first term. 1 over 2. What's 2 squared?
4,
Alright, 1 over,
9,
alright, and 1 over, what would be the last term?
100.
Alright, 1 over 100. So I put an equals, I can't put an equals when I can do a what?
Similar.
Yeah, it's squiggle. Right, this series, if I use n equals 10 terms, I put from this. Hey, there's a notation for this. This is called S sub 10. It means a partial sum. I did an S sub 10. I'm saying I did a partial sum of 10 terms. And it's coming out to be, if anybody wants a couple ways to hit this on a calculator, can't you just type this on a blank screen? Yeah. Crank it up. I'll let you see this. You're okay there, right? Yeah. Nice. So what I'll do is I'll pull this down. And there's just some ways you can play around with your calculator. Because you might want to just not add that up on a blank screen, right? You might say, can I look at these on a list? Of course you could use Microsoft Excel. But sometimes there's some other neat ways you can deal with this. With that light to pop up. Or we're just going to add up the first 10 terms and see what we get. I can tell some people already got it. Look, there's different ways you can use this calculator. Alright. Everyone see that thing? Is it showing up okay? So what I'm going to do, if you like playing around, I just don't feel like adding this up on the blank screen, right? So what I'm going to do is I'm going to hit this stat button right here. Don't see stat? And then there's something called edit. I'm just going to hit enter. You see these lists? Well, what can I do in list 1? I can enter the numbers what? Here I go. 1, enter 2, 3, 4, 5, 6, 7, 8, 9, and 10. Do it slow. Come on. There we go. And then I can arrow over here, but I don't want to rush you. I want to wait till everyone does that. I'll just add, put 1, 2, 3, 4, 5, 6. It's just one way I can do this. Now, if you like your calculators, you can stay organized. Now, I'm going to go to L2, and you know what I'm going to tell L2 to do? I want it to do what for each one of those numbers I use? Because I'm going to plug in a 1, but I want it to take 1 over and square that number, right? So I'm going to go over to L2, and watch me carefully. I'm going to up arrow here and highlight L2, and I'm going to type 1 division L1 squared. Okay? That's what I'm going to type. 1 division bar. Where is L1 on the screen? You got to hit second 1. Does everyone see that? But I want to raise it to what power? Raise it to the second. And what will it do when I hit enter? It's magic. Ooh, thank you. Isn't that cool? So I just wanted to do that for me. So if you like doing this, now some people go, well, forget this, I'll just put it on a blank screen. But I just want to now get all this added up. So I'm going to hit second mode. Was everyone okay with that? Connor, did that work all right?
No, it's giving me an error message. It's fine.
Oh, okay. I can show you later.
Okay.
Hey, so I'm just going to blank out of here, Connor and everyone. I'll just, how do you hit get out of the screen? Just second mode, right? Quit. And I am going to go to a menu called list. It's second stat. Second stat. And there's an operation, see that names, ops, and math? I'm going to arrow over to math. And look what number 5 says. Number 5 says what? It says sum. All right, I want to sum something. What do I want to sum? Which list? You so I'm gonna put in an L2. So to do L2, I gotta hit second. Now, if this you found annoying, you could just add these up on the blank screen. Or you might prefer Microsoft Excel, but since we had to add up all these terms, what do we get? 1 point, I better write this down. 1.5497 677. Cool. Love it.
Just do math. Yeah, that's what I was gonna say.
Math 0, you can do that. Yep, absolutely. That's totally fine. Hey, is everyone okay with that?
Nice.
Hey, so now, I want to talk about that math 0. I just want to up arrow here. It's a summation button. Everyone see that? If you have it. Now, not everyone has a what? Math 0. This is an upgraded calculator, so that's why I wanted to show that. Like, raise a hand. Who's got a TID3? Yeah, they don't have that, you know, in terms of that summation thing. So they got to go through this method. But Math 0 has a what? A summation button. It was Math 0. And you go, oh, if my calculator has that, I want to hit it, and look what it shows. You hit enter, and it's got everything, and I just type everything in, right? I can use X here, true? X, I could put a 1. How far did I go up to? Oh, up over here, up arrow there. I'm going to put a 10. And let me right arrow. What was in this expression? 1 divided by X caret. I'll just tip what? Cool. Who's got the newer models? You might find that a lot easier. You didn't have to go into L1. Absolutely do that. Awesome. Now, what's this remainder theorem say? If we use 10 terms, then a 10th remainder must be less than the, we use 10 terms, must be less than or equal to this. So I'm going to hit the lights and I'll come back to the screen. I just want to get the lights up here. This remainder theorem is very simple. Very simple to understand. It's saying if I use 10 terms, then the remainder, the error in this problem has to be less than or equal to this. And I'm using 1 over x squared because that's like that p series. The only thing is, what was this antiderivative? Can you help me evaluate this? It's an improper integral. What we're saying is the remainder, the error for what we just found out, how close is this to the actual sum? We can estimate it. It's got to be less than or equal to this. What is that integral? So that's going to be a negative 1 over x, the antiderivative. Okay. And I got to go from t to a what? A 10. I'll send my limit towards infinity. And you get what? You get a 0, subtraction of 1 over 10, which becomes a what? 1 over 10. So, what is that? You might want to look at this as a decimal. What's that as a decimal? 0.1. This is what we're saying. This was pretty close to the actual sum. The error, we're like within 0.1. We know the error is within 0.1. Pretty cool, huh? That's 1 decimal place. We only did how many terms? 10 terms, right? So I just want to point out, we're within this what? 0.1 here. So, what I could do is I'm going to leave this up here. We know it's got to be within what? 0.1 or 1/10 of the actual sum. But this is like an upper bound. So there's the upper bound. Can you go over here? Can everyone read what it says right there? Same thing, but it says integral starts at, you see it says n plus 1? So if I used n equal to 10 here, n equal to 10 here, right now I'm saying, okay, this is really close to the actual sum, which we don't know, but it's within 0.1 of the actual answer. What would be a lower bound? I'm like, well, let's go in. I'm going to make this 11, okay? So I'll do that. Now, if you got the TI-83, you know what to do. You're going to have to go on the list and do that. And I'll hit the light. So I want to do this in case I got my TI-83 people here, but some of you might just do what? 1 to 11. Does anybody know how to make that re-emerge on a screen and you can just change it? Upper. Second enter. So if you want to, you could hit second enter. I'll hit the second enter. Can re-emerge what you just had. It allows you to edit it. So I'm going to do that. But if you got the TI-83, you're going to have to go back to the list and add an 11 in there and do this. Now, which number do I want to change? I want to change to what? change this to a 11, right? Hit enter. Okay, now I got a 1.1. 558. All right. So 11 terms it'd be what? 1.558? Is that okay with that? 1.558, what was the other number? The 1.449, true? Want to make sure I got the same number there. That's cool. But what we're doing is, I'm going to write this another way. I'll hit this light here. I'll turn this off. This is the last thing before we do this. This was 0.1, right? You know what R11 be? We get this equal to what? You never go from 11 to infinity? Can you help me do that? What would you get for that error? 1 over 11. By seeing this, we know we're going to just get what? 1 over 11. So this is what we're saying. I'm saying that this sum right here is going to be between, right? I know it's less than 1.454976771 plus, what was that upper bound? It was what, 0.1? I'll write it for 1 time. And the lower bound is, I'm going to use the same number, 1.549767731 plus 1 over 11. This is what I know. Just by looking at 10 terms. I know that has to be in between these. And I only did 10 terms. No, because we're just looking at like what the error would be in between these. You'll notice, because this number, this is interesting. This is actually lower than it, isn't it? 1 over 11 is smaller than 1 over 10. But you'll notice it gives you a really good range of where that sum would be. We know that that answer right there, I'll put this again, has to be between, hey, can someone do this for me on a calculator? What is that number right there? What's 1.549767731 plus 1 over 11? You know it's got to be somewhere in here. And thanks for being paid. This is kind of fun to do. We're trying to emphasize that when these sums we're dealing with in this whole chapter 11, a lot of them we don't know the answer to unless it's a geometric series.
1.64067.
And that's this one?
Yeah.
1.64067, that's far enough. How about over here? What's this? Oh, I just got to have a 0.1 where? Don't I go with this? And when I know the sum is somewhere in here. And I already looked at how many terms. So I want to label things. What was this? This was the summation to how many terms?
11.
Plus, that was summation of 10 terms, but I looked at that remainder concept, right? So I thought of that, plus R11, and over here I did the summation of 10 terms, but I used the end. Does that make sense? See how this number was from 10 to infinity. This was from 11 to infinity. Remember how we got those two answers?
What do you have two comparison operators? 1.6406 is greater than, less than, equal to?
This means less than or equal to. So we're saying that this is the actual sum, and it means it's got to be between. So how about that, between? It's got to be between.
Oh, okay, so you're 7 kind of look like a comparison, I'm sorry.
Yeah, it's okay. Is everyone okay with that? Cool. Now, there is a mathematician who figured out this sum exactly. His name's Euler. You know what he got it to be? He figured it out as this. Thank you, Euler. He figured this out. He figured out that this summation. It's a p series, right? He figured out that p squared. He proved it. But now we're talking about Euler, one of the greatest mathematicians ever. But he figured out this came out to be exactly pi squared over 6. Now we hit that on the calculator. What's 3.141592665 squared over 6? What do you get? 1.6449 inside there, right? So do you see the idea? Now you might think, oh, so did Euler figure out 1 over n cubed? No. Has anybody figured this out? Exactly. We go to that p-series. Has anybody figured out that p-series exactly? The answer is no. You know? So it's really interesting how it's like a lot of times we're just left what? Estimating. And we can use technology now to estimate this stuff. Be accurate to 8 decimal places. Store it into calculators. Store it into computers and stuff.
Is that the same guy that gave us the e-test?
Yeah, he's the one who said, let's call that E for the natural base. We're going to call that E. And he did a bunch of other things. Oh, yeah. He's brilliant. What's your book again, Chris? What's that cool book you have for calculus?
Oh yeah, the foundations of mental calculus.
For
Euler.
Euler, yeah.
Very cool.
Yeah, shoot.
All right, I want to do the comparison test. And I'm going to start with this one.
Those things pronounced Euler. I guess it's screwed better.
Hey, everyone, 11.4? Let's check out this problem. I'm hoping you love this. I'm hoping you like this. We're now talking about a new test, the comparison test. Didn't we already do this problem? Yeah, but you might find an easier way to look at this problem. Like, hey, you might remember that integral? It was an arctan, it was kind of messy. Maybe I wasn't sure about its limit and stuff. Well, with this problem, what we're saying is, boy, what if we can compare it to something easier? What I mean is, what if I can just get that stupid 9 off there? And I can compare this to 1 over n squared. Isn't that a p-series? And we already know about p-series. Let me hide that. If I hide that right there, and when that p-series, is that convergent or divergent? Convergent, right? P-value is greater than 1, and p-series is greater than or equal to 1. So rather than going through that entire integral test, which was great, and it was nice, what's cool about the comparison test, it can just save me a lot of time in writing. As long as, now this is what has to happen. A sub n, that means this guy, I'm going to call this A sub n. Hey, you're A sub n. And I'm going to compare it to something easier. This guy. So this is who I'm going to compare it to. So, by that, I'm going to call this B sub n. I'm going to call you B sub n. Let's compare it to this. And if this series converges, and A sub n is greater than or equal to B sub n, that will be for divergent. But I want us to focus on, I'm going to put a big dot. If A sub n is less than or equal to B sub n, and if this series converges, then this one will also converge as well. Okay?
So do we just get a B choose what B sub n is?
That's right, you get to choose this.
Okay.
You choose something simple. Something that's really easy.
Do we usually try and make that one based off another rule so it's...
Yeah, something that you can compare to it. So what do you know about 1 over n squared plus 9? And 1 over n squared? Which one's smaller? Sometimes it's hard to tell.
1 over n squared plus 9.
Let's plug in a number. Yeah, a lot of you know. Let's plug in a number. If I plug in a 1, what's that?
1.
1. If I plug in a 1 over here, what do you get?
1/10.
Which one's smaller? Ah, so this one is going to always be less than or equal to this for n equal to 1 and higher, right? That's true. All right, so you're less than this. This is less than this. Well, as long as this guy converges, then this one has to converge. This will converge as long as this converges. Okay? Does this converge?
Yes.
This converges. And so going off what we just said, we chose something easy that was very similar to this. And because A sub n is less than or equal to B sub n, the series A sub n converges Remember, I'm just going to justify this, but I don't have to write as much as I did with that integral test. This series converges by the comparison test. I wonder if I write CT. And let me just write one more thing. I do have to point out why this converged. Why did this converge? This converges by the comparison test because this series right here, do you remember what I called that? B sub n? B sub n converges by what method?
P series.
And I'll put that. P series, P is greater than or equal to a what? 1. Or actually, I'm sorry, P is greater than 1. You were talking about that earlier. I gotta make sure I get that right symbol right there. P series, P just has to be greater than 1. If P equals 1, it diverges, doesn't it? So this act, but everyone check out the writing here. This converges by the comparison test because the series B sub n right here converges. It's a P series with P greater than 1, or P equal to 2. Cool. So I definitely chose something like that.
Would you expect that writing of the test, like that exact wording?
Exactly. I want to. That's what's expected because when I write the directions on a test, I want to point out what I write. I write something like, "Hey, be clear in your justification." So I say number 1. I'll write this. I'll say, "Make sure you name the test." You want to name the test you're using. So in this case, I was using the what? The comparison test. But you can abbreviate it. And then I explain what went on with the comparison test. I said, hey, this converged because by the comparison test, this series I was comparing it to, when we wrote it down, there's P sub n, converged as a P series with P greater than 1. So excellent. Do you notice though, with the integral test, it took a little bit more writing, didn't it? I don't know, you might think it's just as easy. I shouldn't say one's easier than the other. But it gives you another option, doesn't it? It gives you another option. Cool. My only worry about comparison tests is when someone uses it and they got this backwards. See, if that's backwards, then I can't use it. Can I give you an example? I want to give you an example then. We go, oh, I thought I can do this. So, what was the one I did close to this? When I did it 15 minutes ago, I had like an n over n squared plus 2. Remember that? Can you try that? So here's, I'm not like this, like warning, be careful. You can tell how many times I've seen something like this on a test. You're like, oh, this student had it, but they just was missing one thing on here. They're like, professor, I knew it diverged. I go, yeah, but you used the wrong test. They go, I can't use this test? And I'm like, no, because this wasn't true. Or this wasn't true. So I want to just look at something like this. Didn't we do one like this before? Well, obviously, who would you want to compare this to? Remember, Connor, we're trying to look for something that's similar to this, so I'll hide that plus 2. Who could we maybe compare it to? Yeah, he goes, maybe we could compare it to n over n. That way we can see who's less than the other, right? Well, what is this simplified? By the way, do you recall this did diverge by integral test? Does everyone remember? Okay, so we're like, oh, okay, this is 1 over n. And this diverges, doesn't it? This diverges. By what? It's a harmonic series. It's a P series with P equal to what? 1. Here's the trouble, though. What does this say right here? I can use the comparison test. If the series I'm comparing it to diverges, well, what has to hold true?
Yeah, that's what I said.
A sub n has got to be greater than or equal to B sub n. You follow me? And look carefully. Is A sub n greater than or equal to B sub n? That's the trouble. So what I'm saying is I'm not going to use the comparison test on this problem. Connor, do you follow that?
Yeah.
I just want to make sure. So that's the danger. Where you go, but I knew it. Remember this diverged? So someone's saying this diverges by comparison test, and then they justify it this way. And they're like, man, I lost all these points. It's because they're using the wrong test. And it was all because it gave you that little one. That wasn't holding true, right? ASIN, graded this, we're like, no. This is what? This is lower than that. So what I'm saying is, I can't use the comparison set on this problem. I would use the comparison test. What would I use? Use the integral test. The integral test is easy. Great. Hey, there you go, great job at that.